Well, thank you very much to the organizers for organizing this event again here in Pisa. And I'm going to talk about a joint work with Dimitri Ara, Vittoria Zornova, and Martina Rovelli. And I'm going to tell you a little bit about these Steiner omega categories. So let me start by recalling what an omega category actually is. So everything I will say is about strict omega categories, no weak stuff. So a strict, yeah, simple, algebraic, nice. It's a reflective omega graph. So a gadget like this, we have objects. Come here. Right. Objects, one arrow, n minus one arrow, n arrow, all the way up. We have sources. Oh, it's more complicated than expected. Sources, targets, and identities. And some axioms like the target of the target is the target of the source. Think about the two cell. And some axioms about the identity, etc. Okay, this is the data plus another piece of data that are the composition, of course, because we have categories. Composition for any dimension bigger or equal than 0. This is the dimension with which you glue these pieces together, and several axioms of associativity, identity, exchange, etc. There are several ways to say this. You can also define omega categories by enrichment, and they are, of course, equivalent. So, example to keep in mind are the usual drawings of objects, one arrow, two arrows, three arrows, and gluing among them in all the possible way you can imagine. Okay, let me give you some examples and some notable examples. So, probably the most important examples are the disks, and the disk co-represents arrows. So, if you take omega functors from D0 to an omega category, these are precisely the objects. With D1, you have the one arrow, with D2, the two arrows, etc. And if you want to think about omega categories a bit geometrically, you want to have disks and spheres. So you can perform the usual structures that you can perform in topology. And spot the differences is just a kind of the boundary of the disks, right? The -1 sphere is nothing, it's the initial omega category, is empty. S0 is the boundary of the one arrow. S1 is the boundary of the two cell, and etc. Okay? The problem with disks and spheres is that they are graph theoretic. They don't encode compositions. So in order to encode composition, you need some other shapes. One shape that was introduced by Ross Street are orientals. And if you look at them, they kind of encode some kind of directed associativity, right? So we have the point, the arrow, the composition, but directed by a two cell. And the third oriental, or 3, is just an associativity, but with directions. Can be oplux or laps, whatever you choose. Another way, devised by Joyal and others, are theta objects. So theta objects are nice gadgets that encode some basic composition of omega categories. So let me try it, maybe like this. Yeah. So you have some basic composition like this. Yeah, this is too hard. And at each stage, you have some composition in the vertical way that can be of different kinds. So it can be 2 cells, 3 cells, etc. But what you cannot have, what you cannot have is composition that go along, that skip one object or more, right? Everything is contained in between two neighbor objects. And they can have all the possible shapes you can imagine. And these two examples are rich, very rich in structure. And the morphisms between these objects are very complex. So Street devised the notion of a computat to deal a bit with his orientals. There is a notion of a wreath product to talk about the morphisms of real theta subcategory of omega categories. But still, the morphisms are hard to describe. These infinity functions between these objects are complicated and very rich. These objects are all free in a very precise way. So I will use the French terminology. So what Street called computats, French people call polygraph. And the polygraph, so omega graph was already taken, so we need another. Graphs are two categories, what polygraphs are for omega categories. So from a graph, you can freely build a category. And the same kind of gadget works for omega categories. Just as more topological, so in a way it's a bit easier. I won't tell you exactly what the polygraph is, but I will tell you what the omega category freely generated by the polygraph is. So those are exactly the cellular objects, if you want in omega category, if you want to be topological. What does it mean? You have a omega category C, you have a set of arrows of any dimension you want. This set must contain all objects. The objects are a subset of this. And then essentially at each level, you have to generate freely C by the object of E of that dimension. And if you look at this, this is just how you generate a CW complex, right? You have a bunch of, okay, let me try, a bunch of n cells. This is the n truncation of C, so you just forget about all the cell of higher dimension than n. You know how to glue them in a way, what are the sources and the targets. In the n-1 truncation, you add them freely, just means that this square is a pushout. So you are given some n-1 cells, parallel n-1 cells that are source and targets, and you add an cell freely as a pushout. So at each level, you have some kind of universal property of the pushout. That's the idea. In order to deal with this complex notion of free objects and morphism between orientals and theta, etc., Richard Steiner devised a nice theory, which is kind of homological in a way, and it works surprisingly well. His idea was to define these augmenting dialectic complexes, and I will show you how these are linked to omega categories and why they are very important. So an augmented dialectic complex, ADC, is just an augmented complex of abelian groups. So a complex in non-negative degrees with an augmentation and all the differential. And what is this directed? At each level, you have a submonoid Kn plus of the abelian group Kn. And these are called the positivity submonoid. So Steiner's idea is to look at these objects as a kind of some homological trace of an omega category. But given like this, it doesn't make really sense. What we want is to...
Excuse me.
Yes, of course.
Just a question. These submonoids are in relation with the differential somewhere, somehow?
Good point.
Okay. Thank you.
It's not prepared, I swear. Yes?
Can we think of the positivity submonoid in can we think of the positivity submonoids as being the marking of some associated completional set?
It's similar in a way. So now we'll tell you exactly what this positivity means for this homological trace of an omega category. Essentially, we want to think each abelian group of each dimension as free, essentially freely generated by some classes of cells. And just Z, the integers have two generators, -1 and 1. And we want to fix one. So this gives you the class of a cell that generates an omega category Z polygraph, essentially.
So you're fixing the source and the target somehow. The
Exactly. The differential tells you exactly the source and the target, yes. Exactly. So this is just a general definition to have a nice category. So it's locally presentable, it's everything you want, but we want smaller objects with better properties. This is a big category with good properties, but the objects are not what we want. So we restrict to the objects that bears a more interesting connection with omega categories. So we say that an augmented dialectic complex has a basis if essentially at each degree, each Kn, abelian group, is free generated by some elements. So it's a direct sum of z's, of the integers. But then there is the positivity, what I was saying to Eduardo. So each Kn is a free abelian group on some set Bn. So think about a direct sum of for each element of Bn. And then you pick a generator, essentially. So you have z plus z plus z, and in each z, you either choose 1 or minus 1. Essentially, all the information is here. In particular, the basis, if it exists, is unique. It's a property, because you chose the generator for each z, either 1 or minus 1. And this Bn has to be thought as a kind of the class of the generating cells of an omega category. And this will be made precise. So now I will have to tell you, I have to go in some technicalities. Just bear with me with a couple of slides. But it's if you think of these augmented dialectic complexes with basis as some homological trace of an omega category, it makes sense. So for each element, C, that you think as some kind of composition of n cells, because it's how do you think as a composition? Well, it is a linear decomposition, right? So we have a unique decomposition. These lambda b are integers, and b are the elements appearing there. And there is the usual notion of support. Maybe we'll go once. The support are just all the b actually appearing in the decomposition. They are infinite number. It's a linear decomposition. And some lambda will be positive, some lambda will be negative. The b's appearing with positive lambda is the positive support. The b's that have a negative coefficient are called the negative support. All right? And you can write any C as is positive support minus is negative support. I'm not saying anything intelligent here. I'm just saying you have a free abelian group. Any element of the free abelian group, you write it as a linear decomposition of the element of the basis. Some elements have a positive coefficient, some element has a negative coefficient. That's it. What is interesting is that when you apply this to the boundary, because the boundary, if you think of C as some kind of n cell, or a class of an n cell, is supposed to give you the target, which is the positive part, and the source of C. In fact, if C is an element of the basis, there is even a notation for this that I will tell you a little bit more about. But what you have to remember here is that you take the differential of an element, it has a linear decomposition, a positive and a negative part. Right, here's what I want to say. Okay, here is a mistake. This is supposed to be an element of Bn, an element of the basis. So if you have an element of the basis, here you're essentially describing it as a kind of cell. You have a C is the n cell. Then you have the source of C and the target of C. And then you can take the source of the source and the source of the target. So you will have something, if you think of the n cell, something like this. You will have maybe this the source. This composition is, yes, is this, and maybe a target of this kind. This composition is this. And this will be the iterated source and the iterated target. And this is the C, which identifies as a C2 plus minus. Why all this definition? Because there is a notion of unitality that we have to impose. Any cell of an omega category as an iterated source, which is a single object, as an iterated target that is a single object. With complexes, you never know. You can have this as many objects. And this cannot happen if we think of these cells as cells of an omega category. So we want to impose that this guy over here, as a linear decomposition, is just one term. It's an element of the basis of K0. It's not a sum of points. It's just a point. Last definition, I promise. If we take an augmented directed complex with basis, there is a pre-order relation, A less or equal than B, that is defined in this way. Either A is in the, you remember we have the boundary and we can take the negative and positive part. Is in the negative part. So for instance, here, this guy would be A less or equal than B. Is in the negative part of the boundary. Otherwise, if this is A, this could be B. So B is in the positive boundary of A. And if you iterate this, this gives you a pre-order relation. And we say that this augmented directed complex with basis is Steiner if this pre-order relation is actually partial order, so it's antisymmetric, and it's unital. So you have this complex. At each level, you have a basis. This basis has this nice property that it is loop-free, so you cannot have A, B, and A again. You don't repeat the elements of the boundaries if you follow this relationship, and it is unital. So the iterated source and the iterated target are just a single object, not a bunch of objects. Okay, now I come to the link. The main theory of Steiner is that there is an adjunction between omega categories and augmented directed complexes, and the right adjoint, this nu, this lambda stands for linearization, and this nu is a kind of nerve. This nu is fully faithful when restricted to Steiner complexes. So Steiner complexes are really a very faithful trace of omega categories. They are completely algebraic. They are chain complexes, and they encode all the complexity of omega functors. But do we have examples of this? Oh yeah, this is for fun, just to see how this thing is done. And it's really what we said, right? It's at level n, you take the free abelian group generated by the cells, and the composition becomes sum. And the differential is just a target minus source. The category of Steiner complexes is very rich. It's closed under the tensor product, which is the gray tensor product, and under the join, so the join of omega categories. And it contains these spheres, orientals, and element of joyal category theta. And now we have a question. So can we identify the omega categories that are in the essential image of this functor nu by Steiner complexes? So can we characterize the Steiner omega categories? Steiner itself proposed the solution, and he said, use the lambda functor, use the left adjoint, the linearization. Just the definition is a bit awkward, because this C is in the image of some Steiner complex, so with base, loop-free, unital. If its lambda is a basis, its lambda is loop-free, its lambda is atomic, which is a weird definition. And it is a kind of unitality, but at each level, which is very complex to check. So with the other collaborators, we wanted to understand better this thing, and we had to understand better this thing, and give it to properties only dependent on C. Okay. First, we had to understand this basis, this lambda basis, lambda loop-free, and how it relates with polygraphs and other notions of loop-freeness that you can give for omega categories internally, and it behaves very badly. It's always true that if C is free as a polygraph, lambda C as a basis, but the contrary is not true. This is a very complicated example. Don't read it. It's just to say there is an example of C, which is not a polygraph, but the lambda C as a basis. So it's free in the complex sense, but not free in the omega categorical sense. And it's always true that if C is loop-free as an omega category, in a strong sense, then lambda C is loop-free. But the contrary is not true. If you take this very simple example, here you see that as an omega categorical level, F is both in the source of alpha and in the target of alpha. But if you compute what happens in the lambda, what you have is that the boundary of alpha is H plus F minus G minus F. So the F disappears. The class of F disappears. And in fact, the positive boundary of this class of alpha is just H, because F disappeared, which is different from the support of the target of alpha, which is F composed with H. So loop-free and basis are very badly behaved in the complexes. And this guy is also, the lambda of this is even Steiner, but if you apply this new, you don't get this back. You get another omega category. So how to solve this? Well, if you give a nice definition of loop freeness for omega category, which is kind of what you expect, so you have these generators and you say, okay, A is smaller than B. If either A is some source of B, possibly iterated. So for instance, this guy could be an iterated source of the 2-cell, and this guy could be an iterated target of the 2-cell. And if this is a poset, is a partial order, then you say that it's loop-free. Well, with this definition, you can actually show that C is Steiner if and only if, and it is loop-free under this condition. And I stop here.
So thank you, Andrea, for the very nice talk. We have time for one or two very quick questions.
I'm very quick. 2 questions. Very quick. First question, what if you internalize? I mean, for instance, in abelian groups, you get the dot correspondence or something for...
Yeah, I think you get the classical result of...
okay, the dot can.
Yeah, exactly.
Between the simplicial complexes and... Okay.
Bourne, I think Bourne proved...
Bourne also proved for groups.
Yes.
For
but it's the same.
Protomodular categories.
Internal omega categories, internal omega groupoids are isomorphic.
Okay. And second, this was just to understand if I understood. And the question is, did you consider passing schemes? This is theory by Johnson.
Yes. So there is a nice paper, I don't remember by whom relates pasting schemes, computads, and Steiner theory. And there is not one that contains the other, but in the nice case of free, loop free, and some nice properties, they all coincide. So you can use whichever theory you want. Yeah, it's a master thesis, I think, of somebody. No problem.
One more question.
Two super quick questions. Are computads closed under retracts?
Oh, nice question. I don't think so.
So it's not like with simplicial categories where they are the...
Yeah.
Okay.
I think the weird example that C is... oh, maybe no. I have to think about it. I think not, but...
And the second one is, are Steiner complexes dense inside omega cat?
Yeah, even finite Steiner complexes.
That's what I thought, because they have theta, right?
Exactly.
Okay.
Exactly. Yeah, that's how you get a great tensor product and join if you want by exactly by extension by the.
So we stop here. So thanks, Andrea, again.